Another situation you could run into when doing this method of decomposing rational functions is you might run into a factor in the denominator that is an irreducible quadratic factor. And being irreducible is just in terms of, say, integers or rational values rather than complex values. Because if you have a term in the denominator like x squared plus 1, technically could reduce into x plus I times x minus I, which is in the field of complex numbers. But we don't want to go into complex numbers. We want to stay in real valued variables here. So in that sense, this is irreducible. Now, you can have irreducible quadratics, but anytime you have a cubic, you can always rewrite a cubic. So long as it has real coefficients, you can write it as the product of a linear and potentially another, well, all three linear factors or one linear and one irreducible quadratic. So this is the last case we really have to handle, which is nice. Now, I'm also going to handle the situation where if you have irreducible quadratic factors that are repeated, you handle those just like repeated linear factors. So for instance, you take your irreducible quadratic to the first power and then add another function, or rational, I should say, with the denominator of your irreducible squared and so forth. So handling that just like the repeated linears. The only difference is in the numerator. We do express the numerator as a linear function. And that comes down to, again, the reasoning behind, you could potentially end up with, or I should say you could still potentially have a proper rational function if the numerator here was at most linear. So anyhow, this is the way we would treat it. So let me walk you through this next example. Here we have the integral of 2x minus 3 over x cubed plus x. I'm going to integrate that with respect to x. So the first step in this process is to factor that denominator. So factoring that denominator, you might want to just kind of go off to the side and take care of that. So x cubed plus x could be written as x times x squared plus 1. Just pulling out a common factor of x here. Now, with that, that leaves me a linear times a quadratic that's irreducible. So what I'm going to do is leave that as is, and then I'm going to take the original 2x minus 3 over x cubed plus x and make up my guess as to what the form of the decomposed rational should look like. So for instance, I have this first factor x, and it's a linear. So I treat it just like it did in the past. So just put a constant over that value. Now I have this irreducible quadratic. And to handle that, I can't just put a constant up in the numerator. What I need to do is put a linear function up in the numerator. So I'll just make it look like this, bx plus c. So that gives me three coefficients that I need to solve for, and the process I start with is still the same. So multiplying everything through by that denominator, which on the left-hand side, of course, cancels out the denominator. So I left with 2x minus 3 there, equals a times x squared plus 1, because the x cancels. And then the complete numerator, in parentheses, bx plus c times the remaining factor in the denominator, x. Now this is important to use these parentheses because this x is going to distribute to both of these terms. And if you didn't do that, then you're going to end up with incorrect values when you solve that algebraically. Now, going about solving this is still the same process. Try and choose strategic values of x that you can first to make things work out as simply as possible for some of the zeros. It's not going to work for all of them, but you can get some completed. So if I let x equal 0, I'm going to have, so 2x minus 3 would become just negative 3. And then this would be a times x squared plus 1, so 0 squared plus 1 is just 1. And then bx plus c times x. That whole term is going to go to 0 because when x is 0, 0 times this whole linear becomes 0. So in fact, we very easily determine that a is equal to negative 3. Okay. Now, there is not a value of x that's going to cancel out anything in this term. Here's the problem. Anytime you square a number, like negative 1 looks like a potential candidate here, but negative 1 squared is positive 1. 1 plus 1 is 2. Anytime you square a number, you're going to get a positive number. And a positive number plus another positive is going to be even more positive. There's no way to get that to cancel out to 0. So here's what we're going to need to do. First off, we can take the knowledge of a being negative 3 and use that to our advantage. So let's just plug that in. All right, so I'm taking this equation here and going to write this as 2x minus 3 equals negative 3 times the quantity x squared plus 1 plus the quantity bx plus c times x. Now, this equation I am free to manipulate in any way that I see fit. All right, so here's what I'm going to do. I'm going to first distribute the negative 3 and the x. So that would give me 2x minus 3 equals negative 3x squared minus 3 plus bx squared plus cx. Now, everything with no b or c term, I'm going to get it to one side. All right, so this is going to well, when I move the negative 3x squared over, that's going to give me positive 3x squared plus 2x. And, well, in fact, if I add 3 over here and add 3 there, that's just going to cancel, so that will disappear. So then that's left and equal to bx squared plus cx. Now, there's a couple of choices I could go about here. Number one is I could choose random values of x, plug those in at this point, and then get a couple of different equations involving b and c, and then I can solve those simultaneously, and that will solve for b and c. But here's another thing, and this was that other method that I talked about at the very beginning, called the method of equated coefficients. The idea here is, in order for these two polynomials to be equal, the only way that they're going to be equal is if, because they're the same degree, the only way they're going to be equal is if their coefficients are equal. So, for instance, the x squared term, okay, the coefficients have to match in the x squared term. Well, that actually kind of makes it look almost trivial, and it almost is. In this case, b has to be equal to 3 because that's the only way for the x squared term to match up. And the same is true for c. So here I can very quickly determine that c has to be equal to 2 because I need something times x, and over here that's supposed to be equal to 2x. So the method of equated coefficients, even though it can sound daunting, it can be actually quite trivial, and that's nice. Now, I generally don't go for that method first, and because if you don't solve for any of your initial values to start with, there's generally a little bit more algebra involved. So like this knowledge of this negative 3 here really is what made that process much easier. If I didn't have one of these 3 to start with, then there's more terms involved and you don't necessarily end up with just b equals 3 and c equals 2. You might come out to b equals 2a minus 5, and then you have to figure out what a is else some other way. So when it works, it generally works great though. But this is the process. Get your easy ones first with strategic values of x, and then go to methods like equated coefficients and so forth. Okay, now, where we're at in the problem at this point is we have this integral rewritten as, let's see, a over x, so that's going to be negative 3 over x, and then b is 3, so 3x plus c, which is 2, all over x squared plus 1 dx. Okay. Now, in order to finish this problem out, here's something that very often ends up occurring. So one of these terms is very straightforward. It will integrate simply as negative 3 times the natural log of absolute x. And we're finished there, so that term's finished. This term, however, is a bit more complex. So it's another rational function. Now don't get worried, it's not like we're going to have to use decomposition again. In fact, it won't decompose any further because it's, this is a factored denominator and we can't decompose it any further. So one thing we can rely on is if the numerator happens to be the derivative of the denominator. So for instance, if I was to let u be the denominator, then du would be 2x dx in this case. Well, I need the numerator to be just 2x and not 3x plus 2. If this was the case, I could use the natural log rule and go on about my merry way, but I can't. But it does give me a clue as to what I can do. So I need a numerator that just has a factor similar to 2x. I can actually get something like that if I decompose this fraction about the numerator. Because remember from the very beginning, decomposing a fraction about the numerator is very easy. You can just split that up freely. So I could write this as, oops, I guess I went back to my original, sorry about that. Thinking and writing. Okay, so this is already solved, so natural log absolute x. Okay, plus, I hope I have enough space to write this, the integral 3x over x squared plus 1 plus 2 over x squared plus 1. There we go. I had to write small. Now, that right there, that does give me a situation that I can use this u substitution here. So if I did let u equal x squared plus 1, du is now, needs to be 2x dx, but it could, 3x is not that far off. In fact, if I just pulled the 3 out and then divide by 2 here, everything's fine. So I can use the natural log rule to solve this. So I will do that. I will use the natural log rule. This other part, this is one that you should recognize. In fact, this is a technique that generally occurs with these irreducible quadratics, is that you end up with a last term here that needs to be integrated using your arctan rule. So this setup right here, this can be integrated using that arctan rule. So I'm running out of space, so hopefully we're almost done. I think we can finish it off here. All right, so this right here, I'm going to have the 3 on the outside. Okay, so that's going to pull out. And then I have this multiplier of 2. So that's where I'm getting this 3 halves multiplier. So I'm going to go ahead and write that. Multiplier of 3 halves. And then That's then in the form of the natural log, so it's going to just be the natural log of the absolute of u, which is x squared plus 1, that part in the denominator. Okay, so that's done. And then this last one. So here, if you'll remember this arctangent rule, you have some function u, which if you square gives you this term, so that's just x. And then some constant a, which if you square gives you this term. And then it's, 1 over a times arctangent of u over a plus c. So there's a formula for it. So you need to make sure you remember that formula. That's going to get used quite a bit in these situations. But I don't need this 2 up here, so it will come outside the integral. And I will have arctangent of x over 1, so that's just x, plus c. And then I have my final answer here. Okay, now I have another example where I don't want us to actually do the integration in the end. The integration actually would be very similar to what we did here, but the steps involved in getting to the integral is a little bit more complicated in this problem, and so I want to do that particular situation. Okay, so we just want to decompose the fraction 1 over x cubed minus 8. Now, x cubed minus 8, this right here, you may or may not remember. There's a formula for, well, I guess I should say, there's one for the difference of squares, and then there's 2 formulas for the sum of cubes and the difference of cubes. All right, this is actually the difference of cubes. Okay, and not everyone always remembers this formula. The difference of squares is easy, but the difference of cubes is a little bit more involved. But it has the same kind of structure. What it looks like is these 2 terms right here. And actually, I'm going to do this. I'm going to leave that. I'm not going to put a plus or minus in there just yet. All right, and then it has another term that looks like a squared, and then you have ab, and then over here you have b squared. Okay, now, generally, students will recall at least this much of the structure, but then it's a little bit tricky to remember what are the different signs involved. So the thing is, for the difference of squares, I'm sorry, not the difference of squares, the difference of cubes or the sum of cubes, whichever one you have here. You can remember this through the mnemonic SOAP, not SAP, but SOAP. All right, meaning that this sign is the same as what you start with. This sign is the opposite, and this last one is always positive. Okay, so that's a way of remembering this, and that's a good thing to have because you may run into these situations, as these are considered fairly straightforward cubics to factor. So that means 1 over x cubed minus 8 is going to look like, let's see, it would be x minus 2. I guess I should leave a little more space in the numerator. And then it's going to be x squared, and then it's the opposite sign of this, so then plus, then 2 times x, and this one's always positive, and then b squared, so that would be 4. All right, so I'm just letting a, of course, be x, and b be 2, because that's the cube root of 8. All right, so that's the factorization. All right, and we're on our way to decomposing this fraction. Here's what the decomposition would look like to start with. So we would have some constant over the linear term, x minus 2, and then we would have x squared plus 2x plus 4 in the denominator here, and we would have a linear function in the numerator there, because that's an irreducible quadratic. Okay, next up here, in solving, the first thing we would want to do is, of course, multiply everything through by the denominator. So that leaves me just 1 over here on the left-hand side. Then a times the quadratic, so x squared plus 2x plus 4. And b, x plus c in parentheses, that's important, times the quantity x minus 2. And that's important that that's also in parentheses because it's the whole value times this entire value, which we're going to have to FOIL to work through. Okay, so easy values to determine first. If I were to let x equal 2, that should get me somewhere. So that gives me 1 equals a times, let's see, 4 plus 4 plus 4, so that's 12. And this whole term goes to 0, because this would be 2b plus c times 0. So we get a equals 112. All right, now that's a good start, but we don't have any other strategic values of x that we could work with. So I need to start working on a method similar to the method of equated coefficients. So plug in the 1/12 for a. So I'm just going to take this original and write it as 1 equals 1/12 x squared plus 2x plus 4 plus bx plus c times x minus 2. And I want to reduce this as much as possible. I want to get just expanded polynomials on both sides. So first thing I'm going to do is, I suppose, multiply everything through by 12. I'm not sure if that's a great thing to do or not, but I think I'll do that. So that would be 12 equals x squared plus 2x plus 4 plus 12 times, and then I'm going to FOIL this, so that would be bx squared plus cx minus 2bx minus 2c. And everything that doesn't have b or c on it will stay on, will go to the other side, and everything with that will stay on this where it's at. So x squared is going to move to the other side, as well as the 2x. Then I'm going to subtract 4 from both sides, so that'll be plus 8 equals 12bx squared plus 12cx minus 24bx minus 24c. Okay, now equated coefficients. Here's the thing. It's not going to be quite as easy as it was this last time. Well, actually, it might be in this case. Sometimes it is, sometimes it isn't. But the thing is, I've got this middle term with x, and I can factor out an x and write this as, say, like 12c minus 24b all times x minus 24c. All right, so when I equate coefficients, I can say this 12b is equal to this negative over here. Oh, I missed that square there. And then this, tell you what, let me use a different color so you can see how I'm equating. That would be equal to negative 2, and also this negative 24. Well, actually, sorry, negative 24c would be equal to 8. Now, if I just need to solve for b and c, the best ones would be to use the x squared term and the constant term, because this middle term uses both of them, and it wouldn't be as easy to solve. But I can say at this point 12b is equal to negative 1. So b is negative 1/12. And negative 24c is equal to 8. So c would be 8, or a negative 8 over 24. And if I factor 8 out of both of those, it looks like negative 1/3. So my decomposition of 1 over x cubed plus 8, this thing could be written as, I'll just do it, 1/12 over x plus, and then it was, oh, I'm sorry, not over x. I should have scrolled up to c. That was from the previous problem. So a over x minus 2, so 1/12 over x minus 2 plus b, which is negative 1/12 times x plus c all over x squared plus 2x plus 4. Now, at this point, we would be able to integrate. But the integration is going to be very similar to the previous integration, so I'm not going to do a separate example for this. It would get a little bit more involved. This denominator initially is not a perfect square trinomial, so you would need to rewrite this as a perfect square trinomial and in order to use your arctangent rule. So it gets a little bit more involved for that reason, but ultimately it would be basically the same as the previous. Okay, one more example in this video, and this time I'm actually not going to do the decomposition at all. I'm just going to set it up. So in example 6 here, I just want to set up the partial fraction decomposition for this term. So in setting that up, I'm just looking for the guess as to what this would look like. Okay, so it puts all the different types of decomposition rules that we have together. So we have, to start with, this x plus 2, which is a linear term. So we would have a constant over that linear term. Okay, so a over x plus 2. Now, moving on to the next, which is x minus 3 quantity squared. So that is linear, but it's repeated linear. So we would do two separate fractions, each with a constant above it, but increasing the degree of the denominator each time. Okay. And then lastly, we have a irreducible quadratic, but it is also repeated. So we do the same sort of thing. We do like, oh, I guess I'm on D here. dx plus e, so a linear, over the x squared plus 4, so to the first power. And then because it's a repeated quadratic, we do another one, but with x squared plus 4 quantity squared. But again, another linear on top of that. So it's the same pattern, but it's the linear on top instead of a constant. And that's as tricky as those can get. We're not going to solve this. It would take quite a bit of algebra to do, but I just wanted to show you the structure of how you might do that if you were ever asked. Okay.